Hello, everyone. I'm Olympia. Thank you for being here with me in this wonderful place called Lights Out Library. And I have a great story to tell you. Tonight, we're going to take a journey to visit two planets in our solar system, Mercury and Venus, the two innermost planets. They are the closest to the Sun. But first, I would like to let you know that we have a Patreon page for those of you who wish to and can support this project. Get more of it and listen ad-free on your favorite podcast app. Patreon is a platform that allows you to contribute directly to our work financially. Our least expensive tier is $3.50 per month, but it doesn't mean you will get less. We let people contribute what they wish or can, and everyone gets everything that is on our page, because the world is a better place when the sun shines for everyone. You will gain access to 23 exclusive episodes, and we add a new one every month. And you can listen and download all the episodes with and without background sounds. And as a token of gratitude, we offer advance releases to our patrons. We have added links to Patreon as well as links to different streaming options, which may be better suited for you. You will find them in the description of the episode. But now, before we begin, if you wish to, you may close your eyes and allow yourself to forget about any worries. Assume a comfortable position, maybe move a bit to settle. Take a long, deep, relaxing breath. And when you slowly exhale, feel your shoulders drop. Release the tension in your neck. Let your face soften and your jaw relax. Make sure your fingers are not clenched and that your legs are relaxed too. And allow the sound of my voice to guide you through this journey. And now, off we go. The first leg of our trip begins close to the sun, near the smallest and fastest planet of the system, Mercury. Mercury is only about twice as big as the Earth's moon, and there are satellites that are actually bigger than Mercury, like Ganymede, the moon of Jupiter, or Titan, the moon of Saturn, both of which we have explored in past stories, and you will find them in the library. But Mercury is considered to be a planet because it follows its own orbit around the Sun. It is not the satellite of another planet. Its mass is also greater than any of these satellites because Mercury is denser, with a density similar to Earth's. It is believed that Mercury is made mainly of metal, 75% iron in fact, and the rest, about 30%, silicate material, what we generally call rock. As we're going to see, conditions on the surface of Mercury are strongly influenced by its proximity to the Sun. But how close to the Sun is Mercury exactly? On average, the distance is about 35 million miles, or 58 million kilometers. For comparison, the Sun has a diameter of almost 1.4 million kilometers, or 865,000 miles. So it's actually not that close proportionally. If the sun were the size of a basketball, then Mercury would be a small grain of sand, but several steps away from the basketball. Still, this raises a question. If Mercury is comparatively very small, but with an enormous mass, the Sun, after all, has a huge gravity well, which is the amount of gravitational pull an object in space is able to exert. How does Mercury keep its distance from the Sun instead of being pulled into it and swallowed whole? This brings us to the subject of speed and orbits. Mercury travels in space around the Sun at a high speed. Its velocity is 48 kilometers per second, about 30 miles per second. By comparison, Earth travels at 30 kilometers per second. The general rule is that the farther the planets are from the Sun, the slower they are on their orbits. The farthest one, Neptune, travels at only 5.4 kilometers per second, almost 10 times less than Mercury. And this is not a coincidence, because an orbit results from an equilibrium. There are two main variables to consider in a star system like ours when it comes to orbits. There is the gravitational pull of the huge mass that is at its center, which pulls the planet. And then there is the object's velocity, which tends to push it away. It is a centrifugal force. Without the mass of the star at the center pulling them, planets would just escape. Their speed would surpass what is called the escape velocity, which is to say the speed above which an object can break free from the gravitational pull of another body. Their orbits form thanks to this equilibrium. The balanced push and pull between the two bodies. There are bodies that sometimes do escape the systems where they first appeared and travel between stars, sometimes even between planets. We know there are lone planets, which most probably formed in a star system and were expelled from it, because even though orbits can last for hundreds of millions of years, billions even, they can be altered by other bodies, sometimes that, for example, can make a planet or a satellite accelerate and break free. This equilibrium does not mean that the orbit is a perfect circle or that the speed is constant. Most orbits are actually elliptical. They look more or less oval, and that's particularly the case with Mercury. When the planet comes closer to the Sun, the gravitational pull tends to make it accelerate, which means that it is pushed away. Its higher speed allows it to go farther from the Sun, but not far enough and fast enough to break free from it. So, after traveling, following a curve that makes it move away, it is pulled back, it reaccelerates, and so on. The cycle repeats itself. In the case of Mercury, it repeats itself in 88 of our Earth days. So the Mercurian year, One revolution around the sun is 4 times shorter than that on Earth. Now, when we say that planets like Mercury revolve around the sun, that is true, but it is not 100% accurate. What planets and everything in the system revolve around is not the star itself, but around the center of mass. The sun accounts for more than 99% of this mass. 99.8% to be precise. So obviously it determines very strongly the center of mass. But the real center of mass in the system is not the center of the sun. Each planet also has a little gravitational pull and drags the center of mass towards it. Of these planetary influences, the most important one in our solar system is by far Jupiter, because it is the largest planet. Jupiter is, in fact, more massive than all other planets combined. Now, as it happens, the center of mass is generally inside the sun because planets are scattered around it, so their respective pools tend to cancel each other. But sometimes the center of mass can be outside the sun. If we imagine an extreme case, for example, when all planets in our solar system are on the same side of the sun, and as a result, all pull more or less in the same direction, which is something that can happen if all planets were to be aligned on the same side, the center of mass could be at a distance of 2 suns' radius from the sun, or 1 diameter. It is not much in galactic terms, but it does lead to another geeky question. How often, if ever, are the 8 planets of the solar system aligned on the same side of the sun? Actually, this is extremely rare, and technically, the 8 planets cannot be perfectly aligned because their orbits are not exactly on the same plane. They are slightly tilted. So at no point could we draw a straight line that would go through the centers of each planet because they are in different planes. But if we simplify and just imagine that the planets are aligned, looking at the solar system from above, we can see that it probably never happened and is unlikely to ever happen before our solar system disappears. Why? Because an alignment of just the 3 innermost planets of the system, Mercury, Venus, and Earth, happens only once every 40 years. The chance of having Mars, the 4th planet, on the same arc at this precise moment is minuscule, and the alignment of the first 4 planets is only possible once every several thousand years. And as you add more planets, Jupiter, Saturn, Uranus, Neptune, which are slower and slower, with larger and larger orbits, the probability that they could all align in the same arc at the same time decreases very quickly. In other words, the number of passes you have to wait for this alignment to happen increases exponentially. I found a paper by a mathematician who calculated that the alignment of the 8 planets could only happen once every 400 billion years. But the solar system is thought to be only 4.5 billion years, almost a 300 times less than that. And, following the Big Bang theory, the universe as a whole is less than 14 billion years old. So it is unlikely that the alignment of the 8 planets that can happen every 400 billion years ever took place in the first 4.5 billion years of the solar system. Maybe the odds are around 1%. Also, the odds are that it will not happen before the sun dies and the system disappears with it. But still, the point was to tell you that the center of mass moved a bit over time, and that this is the real pivot around which planets revolve. Okay, so now let's take a look at Mercury itself. Like other rocky planets, Mercury has a solid crust and a disassociated structure inside, meaning that elements are organized in layers with a mantle and a core. And as you approach the center of the planet, pressure and temperature increase. I mentioned earlier that Mercury is 70% metal and that it contains proportionally a lot more iron than any other planet in the solar system. This is a bit of a mystery in itself because why would a particular planet accumulate a lot more iron than others in its formation process? Rocky matter in the solar system has a certain ratio of silicate and metal that can also be found in rocky planets like Earth or Mars. So why does Mercury differ in its composition? The first theory to explain this, most widely accepted at this point, is that Mercury was once bigger than it is now, several billion years ago. And at that time, its mass would have been more than twice its current mass, with a metal-silicate ratio similar to other rocky planets. But the solar system was still in its early stages, and there would have been a collision with a planetesimal. That is to say, a fairly large object formed by the aggregation of rocks and dust that crossed Mercury's trajectory. Based on models, this planetesimal would have been several thousand kilometers across and about 1/6 of Mercury's mass. The collision between the two objects would have been cataclysmic and would have stripped away much of Mercury's original crust and mantle, that is to say, its rocky components. So Mercury, as a result, would be so rich in metal, not because it attracted more iron than other planets, but because it used to be a bigger planet that lost much of its rock and kept its metal. But this is just a hypothesis, and there are others. The second one has the same starting point. Mercury was more than twice as massive in the early stages of our solar system than it is today. But the loss of its rocky material would not have come from the collision, but rather from solar activity. The proto-sun, which was still forming, would have been larger than today. Its gravitation made it contract to its current size over millions of years. So the sun would have been larger at the time, and as a result, temperatures near Mercury would have been around several thousand degrees. This would have vaporized the rock at Mercury's surface, forming an atmosphere of rock vapor. And this atmosphere would have been lost, carried away by solar wind, that is to say, the stream of particles that the sun produces. So this is yet another potential explanation for the loss of Mercury's rock that would explain why it contains so much metal proportionally. The third hypothesis proposes that Mercury formed as a metal-rich planet from the start because of its proximity to the sun. The huge cloud of gas that would have become the sun would have caused drag on the particles from which Mercury was accreting. This would have made lighter particles to be expelled and swallowed by the sun, instead of being gathered by Mercury, whereas heavier metallic particles would have remained available. And as a result, Mercury would have ended up with more metal than rock in its structure. In any case, this happened several billion years ago, and today Mercury presents a surface that is similar in appearance to that of the Moon, with large plains and a lot of craters, which always indicates that the body is geologically inactive. The surface material is not renewed by volcanism or plate tectonics like on Earth, but instead it remains static, and only impacts from asteroids can modify its appearance. Due to the proximity of the sun, it makes sense to anticipate high temperatures on the surface of Mercury, and indeed, this is the case, but only on the parts that are directly exposed to the sun. Mercury can also be an intensely cold place near its equator, and during daytime, on the side of the planet exposed to sunlight, the temperature rises up to 7,000 kelvins, which is about 800 degrees Fahrenheit and more than 400 degrees Celsius, about twice the temperature of a cooking oven. But the same regions at night, when they are plunged into darkness, fall to only 100 kelvins, which is minus 280 Fahrenheit, or minus 173 Celsius. That is to say, cold enough to freeze water instantly. In this episode about Mars, we explore its conditions, which are harsh, but almost welcoming compared to Mercury. And what makes Mercury even more inhospitable is that a day or a night lasts a very long time on the planet. The planet revolves rapidly around the sun, as I told you before, every 88 days. But it rotates. It spins very slowly on its axis, in a way that is locked to the sun. Every time the planet completes 2 revolutions, 2 orbits around the Sun. That is to say, 2 Mercurian years. The planet rotates only 3 times on its axis. For comparison, when the Earth completes 2 orbits, 2 Earth years, it rotates more than 700 times on its axis, but Mercury only 3 times. It is very slow rotating. Another way of saying this is that one single day on Mercury is the same amount of time as 58 Earth days, which also means that any point on the equator of Mercury can remain exposed to the Sun for a very long time. For an equally long time, stay in the dark. 176 days, 2 Mercurian years. The time for the Sun to rise, stay in the sky, and set is actually longer than a year due to this combination of rapid orbital velocity and slow spinning. 1 year on Earth is 365 days, but on Mercury, 1 year is half a day. There are also regions of the planet around the poles that are constantly in the dark or near dark, and where temperatures never rise much. Probes sent in the past decades have shown that there is likely ice, probably water ice, that stays permanently frozen around the poles of Mercury. This shows that, despite its proximity to the Sun, the planet is not just a burning hot desert of plains and craters. The hottest planet of the solar system is actually not Mercury, but Venus. If you find Mercury hostile, just wait for Venus, because it is worse. So let's continue with our journey to our second destination, which is also the second planet from the Sun in our solar system. At first glance, Venus and Earth look like twin planets, almost the same size. Earth is just a touch bigger. The 2 planets are not that far apart, and actually, there may have been a point in the distant past when Venus looked more like Earth than it does today. But nowadays, the condition at their surfaces could not be more different. We saw before that Mercury is just over 36 million miles from the Sun, which is just an average, of course, because its orbit is elliptical. Venus, by comparison, is nearly 109 million kilometers, 68 million miles away, almost twice as far. The orbit of Venus happens between the Sun and the Earth's orbit, and this means that seen from Earth, Venus is never very far from the Sun, and when it is not hidden by the Sun's light, it is not hard to see. After the Sun and the Moon, Venus is the most visible, the brightest object in our sky, and its visibility is increased not just by the relatively short distance on an astronomical scale, but also because of a layer of very reflective clouds in its upper atmosphere. Mercury, the Moon, or Mars barely have an atmosphere compared with Earth. But Venus, on the other hand, has the thickest, densest atmosphere of all the rocky bodies in the solar system. The clouds that enshroud it and make the planet look white when seen from space are composed primarily of sulfuric acid. But this is just a taste of what lies beneath. The atmosphere on Venus's surface is so dense that the pressure is more than 90 times what it is on Earth. For comparison, it is equivalent to the pressure of about being 3,000 feet, 900 meters, underwater. That is an amount of pressure that human bodies cannot stand, obviously. Now there are submarines that reach this depth and deeper, so it's not impossible to imagine a man-made vehicle resisting the pressure on Venus's surface. But an additional problem would be the heat. The mean temperature at the surface is estimated to be more than 700 kelvins, that is 460 degrees Celsius, or 860 degrees Fahrenheit, when exposed directly to the sun. Why is Venus so hot? Again, it's because of the atmosphere. We'll come back to the reasons why Venus ended up with such a dense atmosphere. But if we examine its composition, it is primarily made of carbon dioxide, 96% carbon dioxide, plus 3 to 4% nitrogen, and traces of other elements. And we know it rather well because Venus was one of the first targets of space exploration. In the past, the Soviet Union had an ambitious program to explore Venus in the 1960s, and they sent several probes. And these probes didn't survive long in the atmosphere, given the conditions. But they did last long enough to send back a lot of valuable information. And since then, more and more information about Venus has been collected, including by a NASA with a probe called the Magellan Orbiter. This probe was able to map the surface using radar since it's hidden from visible light. The carbon dioxide at the surface of Venus is in a state that we don't normally encounter on Earth. It is called a supercritical fluid, which means it is not just gas because it is very pressurized. It's also very hot, but not to the point of being solid. It has passed the critical point of pressure and temperature where it could be a gas. But there is not enough pressure to make it a solid, so it exists in an intermediary state beyond the gas and liquid phases. And this is what we call a supercritical fluid. It is believed to be rather common in the atmospheres of gas and ice giants, Jupiter, Saturn, Uranus, Neptune, and also Venus. On Earth, though, supercritical fluids don't normally occur naturally because of a different set of conditions, except maybe for water at the exit of some hydrothermal vents. Hydrothermal vents are like natural chimneys that eject very hot water that is heated by the temperature of the Earth's mantle. This water is very hot, several hundred degrees, when it comes out of the vent. So were this superheated fluid to be ejected at the Earth's surface, it would steam. But at these depths it cannot be steam because there is too much pressure. These vents are deep underwater. This fluid cannot be just liquid either. It's too hot for that. And at the same time, there's not enough pressure to make it solid, to turn it into ice. So instead, like on the surface of Venus, it is in a supercritical state. This doesn't last long, because once it's ejected into the much cooler surrounding water, it cools down quickly and becomes just a liquid. It is hard to imagine the texture of a supercritical fluid. We are not used to it at all, but in any case, you would not want to experience it because if you plunged your hand into a supercritical fluid, your hand would be both burned and crushed at the same time. This gives you an idea of the kind of environment at the surface of Venus. And Venus's atmosphere is also responsible for the heat. It is so dense that it doesn't allow any heat to escape. It creates a massive, extreme greenhouse effect, the strongest we know of in the solar system. Venus did not form with such a thick atmosphere. Typically, the gases that compose the atmosphere on a rocky planet can come from an asteroid impact. They are liberated and stay because of gravitation, or from degassing from the planet's crust and mantle, which is when gas is released at the surface. Typically, what happens with volcanic activity. This atmosphere then stays in place around the planet when the planet is massive enough to retain it due to gravitation, and when it's not carried away or ejected into space by collisions or by solar wind. A magnetic field, like the one that surrounds Earth, also helps to retain its atmosphere. Venus does not have a magnetic field, so gravitation explains how the atmosphere is able to stay with the planet. Earth and Venus have very similar masses. I mentioned that Earth is just a touch more massive. So they also have quite similar gravitational pulls. Given this set of conditions, how did Venus end up with this crushing atmosphere when Earth did not? These are just hypotheses, but studies have suggested that several billions of years ago, Venus could have had an atmosphere similar to Earth's early atmosphere. In these conditions, there could have been substantial quantities of liquid water on the surface. And why not? Life could have appeared in these oceans if they existed. But what would have ultimately doomed Venus would have been its proximity to the Sun. The distance from the Sun to Venus is 70% of the distance from the Sun to Earth. This means Venus receives more energy from the Sun. And as the Sun only gained in luminosity in the first 100 million years of our solar system, any water on Venus would have entirely evaporated. This would have accumulated greenhouse gases in the atmosphere. Water as a gas, as vapor, has a greenhouse effect. And once it passed a critical point of greenhouse effect, the heating of the planet would have snowballed into a loop. The accumulation of heat at the surface would have released even more greenhouse gases, thickening the atmosphere and making it even hotter, and so on in a cycle. At this point, It is hard to imagine any life on the surface of Venus, but if there is any, and this is purely speculative, because we have no solid evidence of life on Venus at this point, it could not be on the surface, but would have to be higher in the atmosphere, in the upper cloud layers of Venus, about 30 miles or 50 kilometers above the surface, because there, temperature and pressure are lower and actually not that far from terrestrial conditions. But this environment is also very acidic, so any form of life in that environment, if they exist, would have to be able to thrive while floating in a type of environment that has no equivalent on Earth. And actually, the clouds are so dense that things could float on them. Venus was one of the first sources of inspiration of terraforming, or at least the installation of human cities on other planets. Another effect of Venus's surrounding atmosphere is that the temperature is about the same everywhere on the planet. There are no large differences between the equator and the poles, like on Earth and other planets. But there are still differences in temperatures due to differences in altitude. Venus has a geography with plains that cover 80% of it, which have a volcanic origin. There are also apparently active volcanoes on Venus, and the sulfuric acid we talked about in the clouds of the upper layers of the atmosphere would have come from volcanic activity. There are also highlands, impact craters too, on the surface, but no small craters because, with such a dense atmosphere, it takes a bigger asteroid to penetrate it and to impact the surface. Many meteorites, like the ones that sometimes strike the Earth's surface, would be destroyed, vaporized, long before impacting Venus. But there are larger impact craters left by bigger asteroids. The images we have from the surface of Venus are not actual photographs. They are radio maps that have been colored in false color, but they still give us a pretty good idea of what the surface looks like. Venus is probably similar to what the Earth would look like with no water, no life of any kind, and constantly plunged in darkness because the sunlight cannot reach the surface. There are so many more things I could say about Venus, but for now, we're going to return to Earth and enjoy the sweet comfort of our beds. I hope you enjoyed our travels today, and that it may awaken your curiosity to learn more about our fascinating universe. It's time to fall asleep, but if you are not sleepy yet, you may pick another story from my ever-growing library. And until we meet again, good night. Sleep well.